vector field. So for a two-dimensional, the vector field F is giving us Pxy on operating the component of the force operating on the x-axis, and then the component of the force or the vector which operates on the y-axis as J. Then when we come to space, 3 dimension, it's made up of the vector field is made up of three components. We have Pxyz, which operates in the x-axis, Qxyz, which operates in the j-axis, and then R, which is made up of xyz, which operates in the k-axis. So these are vector fields. There are a lot of vector fields, but we'll also look at another type of vector fields where we call them conservative vector field. So we'll look at conservative vector fields. So when we say conservative vector fields, what do we mean? So we're going to have vector calculus. We're going to have conservative vector fields. So anytime we hear of conservative vector field, it means there are also set of vector fields either in 2 dimension or 3 dimension, which are generated from a certain scalar function, or we call it potential function. So F is generated from a given scalar function or potential function. So this is potential function. So how do we generate conservative vector field from potential function? We do that by using the symbol called del. So we find the del of F, where the symbol, which is triangle turned upside down, is known as del. Or nabla. And so it gives us this is a scalar function or a potential function, and if you operate it with the nabla or the del, we get the conservative vector field. And that also, if you can get them in on a plane, that is ij plane, and then we can also get it in space, which is ijk, and this is the coordinates. So let's take for example, let's see how we generate a conservative vector field from a given potential function. So let's take an example. So given F to be equal to 4x cubed z5 minus 6 y cubed z to the power 4. Then find f. So given a potential function f, which is 4x cubed z to the power 5 minus 6 y cubed z to the power 4, we are asked to find the conservative vector field f. And so to do that, we need to define the nabla, which is the del. Del for 2 dimension is defined as the partial x I direction plus partial y in the j direction. And then when you are using 3 dimension, then the del is defined as partial xi plus partial yj plus partial z in the k direction. So in this case, we have x, y, z. So we are going to use the three-dimensional, and so it's in space. So we're going to have our f is equal to del f, and del is giving us partial x, partial y, partial z times f. In this case, our f is 4x cubed z5 minus 6y cubed z4. And so we're going to multiply, we're going to have partial x of 4x cubed z5 z raised to the power 5 minus 6y cubed z raised to the power 4 plus partial y for f, which is 4x cubed z raised to 5 minus 6y cubed z4. And the last one is partial z of f, which is 4x cubed z raised to the power 5 minus 6y cubed z4. And so we need to differentiate each of them. So we're going to have, like we learned from partial differentiation, we are differentiating this term with respect to x. So as usual, y and z components are treated as constant. So if you differentiate, so this one will be in the I direction, this one will be in the J direction, and this one will be in the K direction. And so for the I direction, if you differentiate this one with respect to x, we're going to have x cubed 12x squared z raised to the power 5. Then here there is no x term, so 6y cubed z to the power 4 is a constant. If you differentiate a constant, you get 0. So this one will give us in the I direction. Then when you come here, you're going to have, you are differentiating this term with respect to y. Here there's no y term, so 4x cubed z to the power 5 is a constant. If you differentiate a constant, you get 0. Then you come here, get minus 6. If you differentiate y cubed with respect to y, you're going to get times 3y squared. Z raised to the power 4 is a constant. That is J direction. Plus the last one. This term, with respect to Z, you're going to have 20 x cubed z raised to the power 4 minus differentiate this one with respect to z. So we're going to have 24 y cubed z cubed in the K direction. And so to tidy up this one, the potential, out of the potential vector potential function that is given, our conservative vector field now becomes 12x squared z raised to the power 5 I in the I direction. Then positive times negative is negative. Negative into 6 times 3. 6 times 3 is 18. 18 y squared and z raised to the power 4 by 4. And that is in the J direction. Then the last one will be plus 20x cubed z raised to the power 4 minus 24 y cubed z cubed in the K direction. So that is how we generate conservative vector field from a given potential function, which means that all consecutive vector fields are generated from potential functions. And so in the next lecture, we are going to look at how we can get or deduce a potential function if we have been given a conservative vector field. And so this brings us to the end of conservative vector field. Our next lecture, watch out for how to get potential functions from a conservative vector field. Thank you very much, and see you in the next video.